Yep, thank you very much for being here. I'm going to talk about something that is really a big deal to data centers and also to all of us. I'm going to talk about the second most consumed material in the world, namely concrete. It's second only to water. And we're talking about big numbers here. Globally, we produce 30 billion tons of concrete. We spend $440 billion to produce and use them. This is more carbon footprint compared to transportation and agriculture. Just to give you a sense about why concrete is uniquely in this position, 1 cubic meter of concrete has about 300 to 400 kilograms of CO2 embodied within it.
So, the data center industry is growing rapidly. And according to the 2024 market.us market estimates, it's expected to expand by $370 billion by 2030. So that means that our concrete use as an industry is going to skyrocket as well. So this is definitely a commodity that we need to focus our efforts on, because concrete is something that is really, really easy to decarbonize. And Julius and I got together a couple of years back, and we're amazed at how far OCP has come. So today we wanted to share our journey with you and how we are proceeding forward with reducing the carbon intensity of concrete together. So up here on the screen, you see the hyperscaler journey, and Julius and myself got together with some folks from Microsoft and from AWS, and we realized that, hey, we are doing the same things when it comes to concrete emissions reduction. We all benchmarking, we all streamlining our designs, we all testing low carbon concrete. So why not pool our efforts, pool the resources, share the learnings, and then see how far we can get with decarbonizing our concrete.
We believe that AI and data are really important for concrete because of many numbers of reasons that we're going to get to in a minute. We think that AI can accelerate the discovery of lower carbon concrete and can be used to design concrete to better fit the speed of construction that we want for data centers.
So, decarbonizing concrete is quite easy, as I mentioned before, right? The first thing is you reduce cement. But if you look at that picture on the chart, right, cement constitutes a small percentage of the overall volume of concrete. But in general, the emissions from cement contributes 80% the total emissions of concrete. So that's quite a lot. So if we focus on reducing cement, that's the first step to decarbonizing concrete. The next thing is to replace cement with other materials like SEMs, slag, fly ash, etc. Those are greener options. Those are one-for-one replacements, and we can decarbonize quite a bit with that.
Mm-hmm. SCMs, or substitute cementitious materials, are called such because they have cement-like properties. If you mix them with water, they will harden. One of the challenges is that there's not enough of them in the world. They're also very regional and seasonal. Many of them are industrial byproducts. Fly ash comes from coal plants, so depending on the time of the year, the quantities change, the temperatures of the kiln changes, and the properties change. Also, coal from different parts of the world have different geology, so there's quite a bit of a diversity. When you take all of this into account, designing them is really difficult because now you have this high-dimensional space that you're trying to understand, and it's really difficult to do by hand. And this is where we think AI and data are going to be important. Yes, I know what you're thinking. Concrete is really old. It's thousands of years old. However, conventionally, it's only been optimized for 2 factors: strength and cost. Now we care about speed. Now we care about sustainability. So we need to both create data to understand how to optimize these metrics and also learn how we can do better with the existing and novel materials. So let's assume that we can have good data, and this is one of the things that Meta is doing, is developing AI and good data. To express the performance of concrete, it's all about strength. Yeah? Compressive strength is the most important one. However, concrete needs time to develop its strength. And we capture this in what is called the strength curve. It tells you the strength of concrete 1 day after it's poured, 3 days after, 5 days after, 7 days after, 28 days after. For structural strength, the civil engineers would specify this in terms of, I want 4,000 PSI at 28 days. But we care about speed, right? So we want to reach that number as quickly as possible because I want to do the next things. I want to build my A-frames, my power, my cooling, and turn up my IT equipment while I'm still pouring and building the next section of my data hall. One example, let's set a baseline. I can take a high cement content concrete, and yes, it will give you 4,000 PSI in under 1 day. I can start moving my trucks, heavy equipment, other things, populate my data centers, and then move on. But the CO2 is very bad. It's very high. Like I said, 300 to 400 kilograms per meter cube. We could substitute a lot of the cement with other materials. However, it's not going to be as fast. It will be strong if you wait long enough, but now it's a lot slower. Now it takes 5 days, 7 days to get up to strength, during which time you're waiting, you're wondering if it's going to get up to the right strength. Did I mix it enough? Did I pour it in the right speed, and so on? You can win on carbon, that's the belief, but you lose a lot on speed. Okay? But thanks to the systematic data we've been generating with our university partners, AI can design for speed. So here's one that has the same CO2 content as the orange one. The blue one is the better AI designed one. And it sets really fast. If you're into concrete and materials, we're also able to do this without using additives, which are special chemicals that are very expensive but can speed things up. Okay? So this is really quite exciting. We believe that we should win together. And so AI that Meta has developed is open source, and you can download it on GitHub. Okay? The nice thing about this framework is that when I build a data center, there are many pieces that need concrete. Some of them need speed. Some of them don't really need speed. Sidescapes versus technical spaces versus foundation versus duct banks. Now I can use AI to design for each of these use cases and achieve the best trade-off that I can in terms of speed, strength, cost, and carbon emissions. Okay? But it's not only about strength. It's also about what is called fit and finish. You will be moving IT equipment around. You will be building on top of it. You will be pulling racks off. You don't want them to be abrasive. You want the floor to be flat. You want it to be smooth. And therefore, we're doing additional testing together to de-risk the fit and finish aspects of concrete for data centers. And in doing this, we're collaborating with the industry. One way that we're doing so is by working with the American Concrete Institute, which is the governing body, trade association that sets the standards and best practices and empowers its members. We have released the open source, and we have open sourced the AI, which you can download, and some basic systematic data we developed with university partners. And I think that this is a great opportunity for OCP members. We can reduce the carbon footprint of concrete, and as you know, data centers are really, really important, and hopefully we can work together to achieve our common goal.
So we wanted to share a little bit about what we've been doing as hyperscalers. Last year, we shared a white paper that we jointly developed where we set some targets on what we're trying to achieve. There were 3 different phases identified with 3 different levels of greenhouse gas reduction. We want to deliver technology roadmaps to decarbonize concrete. And the only way we can do this is through joint POCs. We want to set standard baselines. We want to be transparent with what we achieve so that we can share it with this industry, but also the industry in general. and then create consistent methodologies so that, Julius talked about long curing times and how we overcome that. So we want to share that information without having to add additives to be able to achieve that. So we approached it by using a phased approach. With phase one, we want to leverage existing technology. We already talked about fly ash and slag. That is, the low-hanging fruit. That's how we're going to decarbonize today. But fly ash is not going to be around forever. Slag is going to change in properties as we transition to electric arc furnaces. And so we'll have to figure out, another way of decarbonizing concrete. And that's where phase two comes in, where we look at more advanced materials like geopolymer concrete, recycled glass, SEMs, as Julius mentioned earlier, LC3, calcinated clay cement. And then phase three is looking at things that are way out there that people are still thinking about or are in laboratory phase, like biogenic materials, graphite, other materials that may even not be thought about today. So that's going to get us the rest of the way, but what we want to do is accelerate that process. So we decided to do a joint pilot, and the goal is to have some meaningful reductions of greenhouse gases. Whatever we learn, as Julius put it, we're going to open source. So the Meta AI is already open sourced. And then as we learn, we're going to open source. So what we've been doing to date is we've been decarbonizing in low-risk areas. Julius mentioned de-risking. We've been doing proofs of concepts in low-risk areas. And where are the low-risk areas within our data centers? It's the outside surfaces where we don't have any structural elements. So we've been trying all sorts of concretes in low-risk areas. The second phase is looking at medium-risk areas, which are outside areas, but they do require some sort of structural integrity. These would be, loading docks that need some sort of rebar, retaining walls, etc. And then, where things really become critical is once you get inside the data center and the data center floor, because that's where we have to be really careful. It's a critical area. We need that require floor flatness, it require finish. And if we can't achieve that with some of these greenhouse gas reduced or greener concrete materials, then we fail as an industry. So what we're doing in this joint pilot is we're picking specific mixes with different greenhouse gas reductions. And then we'll select a site where we want to do a proof of concept on a data center floor. And we're going to try and achieve the floor flatness and the finishes that we require on a data center slab-on-grade application. We'll test the mixes in the laboratory, see the results, use Meta's AI to validate the results and compare the results that we get from the AI model. And then do an actual field placement and then share the results. So hopefully by October, we'll be able to share something concrete, and excuse the pun. So, what does success look like? We want something that's going to be measurable, that we can share to say, hey, we were able to achieve 40% or 60% reduction with some of these new materials. We want to be able to give our general contractors the confidence to be able to use these materials, and the confidence that they are not going to be delayed in their construction, right? Yeah, we are out of time. So our call to action, come join us. We're part of the Data Center Facility Sustainability Track. We talk about this all the time. Look at GitHub for the Meta AI. And share data. If you have data, if you're running POCs, share it with us, because the more data we have, the better our AI models.
And with that, thank you very much. And now we have time for a few questions.
Any questions?
Hi, I'm Jose from AirTrunk. I wanted to ask about how you export these models and these studies to outside of the US, to Europe or to Asia. How you're planning to kind of share that, but understanding the intricacies of each of those locations in terms of concrete industry and availability of resources.
Yeah, I can take this one. So the first aspect is maybe about IP. Concrete suppliers have spent a lot of time developing knowledge and expertise and testing of concrete. And we believe that if we can help them get into a more data-driven design and leverage our open source AI algorithm, then they can develop better mixes that they can then choose whether they want to publish the mixes or keep it within their database. And we are already working today, Meta, with a few concrete suppliers to help them upgrade the way that they work with data. That's one aspect. Second one is the US and Europe, or more precisely Europe versus the rest of the world, the way concrete is designed is quite different. In Europe, it's heavily regulated. The cement suppliers tend to pre-mix the SCMs and then sell them as a labeled product. So in Europe, if you want to innovate, you need to go to the cement suppliers, which are quite few in the world, and then work with them. In the US, it's every supplier, every concrete supplier, and every mixing plant on its own. So it's quite a bit of a difference here in the way that it can be scaled.
I have a question about the transparency. Do you see a way how to make transparent and traceability for the cement itself, according to your input?
Yeah, that's a discussion that we continuously have with manufacturers. Some manufacturers will share with us the materials that go into the cement or the cement replacements. But a lot of them state that they have IP that control the SCM, chemistry, et cetera. So yeah, that is a challenge. And there's no way of getting around it. We're still working our way through it, but Julius, if you wanted to add anything to that.
Yeah, I think number one thing that we as building owners want is data on the performance first, and then the mix maybe second. We're lucky to be in a place today that regulation is coming to encourage it. So for example, the IRA bill in the US does have buy green directives. If you want to bid on projects funded by that bill, you have to disclose the LCA of the concrete mix that you use in the project. And for us, it would be great, for example, to also see the strength curve. So we kind of want performance that we can appreciate and enjoy, such as speed and strength, in addition to carbon emissions.
Andrew Bourget, we're a contractor at ECUS. A few questions regarding your target. I would add a notion of durability. We are designing our structures for 100 years, but you can, of course, design the concrete for 50 years. So I was wondering what durability did you place on your targets for the concrete?
Yeah, the timing does, you are right. The longer you design your concrete for, the better your target. But this is purely looking at greenhouse gas, embodied carbon reduction without looking at the duration your concrete's going to be lasting. Mm-hmm. I think it gets too complicated once you start looking at that, the length of the life of the concrete. And also the targets right now are based off of the NRMCA regional baselines in the US. Here in Europe, my understanding is that concrete is already a little bit more advanced in terms of decarbonization than in the US. Okay. You're already, using fly ash and slag as standard.
For 30 years, yes.
Yeah, as standard constituents, yep.
Maybe I can help you on one subject. The cement companies are cornering the market on calcinated clay.
Yeah.
They foresee the same as automotive, where there'll be penalties and you'll have to buy your way out, so to speak. So they want a means to themselves benefit from this calcinated clay, and they don't want third parties mixing with their product, and they would have to pay full penalty because they can't reduce their own emissions. But Vinci Construction is setting up supply chains independent of the main cement manufacturers. They have the clout to do that. And so I invite you to contact them. There's some interesting stuff taking place in that company.
Sounds good. Thank you for sharing that.
Thank you.
I think we had a couple more questions, but we're out of time, so please do approach Julius and Priya, and I'm sure we can continue the conversation.